For decades, the conventional wisdom in tech was basically that if you wanted a faster database, you just needed to build a faster hard drive.
Right, yeah. Throw more hardware at it.
Exactly. We spent years obsessed with hardware speeds, just assuming that reading data faster was, the ultimate solution to dashboard lag and slow applications. But it turns out the absolute fastest database in the world isn't the one that reads data the fastest.
No, it's really not.
It's the one that knows how to read almost nothing at all. Which is wild to think about. So today, we're looking at this architectural revolution that allows modern analytical engines to scan 1 billion records in milliseconds, largely by, and this is the crazy part, intentionally ignoring like 99% of your data.
It really is a complete paradigm shift. I mean, we spend so much time trying to engineer a faster race car when the actual solution was to completely redesign the highway it drives on.
Yeah.
The physical layout of the data actually matters way more than the raw horsepower of the machine that's reading it.
And that is our mission for today. Welcome to the Deep Dive. We are looking at a really comprehensive breakdown titled Understanding Column-Oriented Databases, the architectural engine behind modern analytics.
It's a great piece.
It really is. And the goal here is to demystify how these systems evolved, from those heavy monolithic software beasts into the lightning fast sort of modular data stacks that run the modern web today.
Right, how they fundamentally reorganized information to bypass physical hardware limits.
Exactly. So for you listening, if you've ever stared at a loading spinner on a business dashboard and wondered why it's taking so long, this is for you. Okay, let's unpack this. Because to understand where we are, I think we have to look at the fundamental flaw in how traditional systems save data to a disk in the first place.
Yeah, we have to talk about traditional databases, the ones that basically ran the world for a long time, like PostgreSQL or MySQL.
Whoa.
They were built on a row-oriented architecture.
Row-oriented, okay.
Right, so if you visualize a vast table of employee data, a row-oriented system writes all the information for employee number 1 onto the physical disk sequentially.
Meaning, their ID, their name, their address, job title, and their salary are all just physically bundled together in one continuous block of storage.
Exactly. They sit right next to each other on the drive.
Yeah.
Which is incredibly efficient if you just want to pull up one single employee's profile to, say, change their address.
Right, because you just grab that one block.
Right. It is perfectly optimized for that exact task, which the industry calls transactional processing. But modern analytics is rarely about individual profiles. Analytics is about massive aggregations.
Right, broad trends.
Right, exactly. So let's say you have 1 billion employee records, and your goal is to find the average salary of everyone who lives in New York City.
Okay, so out of all those fields, name, address, whatever, we literally only care about 2 data points, right? The city and the salary.
Just those 2. But here is the fatal flaw of the row-oriented design when it comes to analytics. The storage engine cannot simply extract just the city and the salary.
Wait, why not?
Because of how hard drives physically read blocks of data, the system actually has to pull the entire row into the computer's memory. So let's say a single employee row is about 500 bytes of data.
Okay.
The engine reads the names, the physical addresses, the phone numbers. It pulls all 500 bytes into the system's RAM, processes it, and then basically throws almost all of it away just to isolate the 4 bytes for the city and the 8 bytes for the salary.
Oh, wow. So for 1 billion records, that is 500 gigabytes of data being pulled off a hard drive to answer a question that only required like 12 gigabytes of actual information?
Exactly. And that disk I/O, that input-output process of moving data from a physical drive into the processor, is traditionally the absolute slowest operation in computing. You are essentially forcing the hardware to read over 40 times more data than necessary.
That is wild. It really is like going to the grocery store. And because you need, a carton of milk, the rules dictate you must physically place every single item from aisle 4 into your shopping cart, push it all the way to the register, and then throw away everything except the milk.
That is a perfect analogy, actually.
It's just a massive waste of energy and time.
Which is exactly why the industry pivoted to the column-oriented approach for analytics. Engines like Vertica, ClickHouse, and DuckDB, they took that massive table and conceptually just flipped it on its side.
Flipped it.
Yeah. Instead of storing a row together, they store each column in its own completely separate isolated file on the disk.
Oh, I see. So the hard drive has one file containing literally just 1 billion names, a totally separate file for 1 billion cities, and another file for 1 billion salaries.
Right. And what's fascinating here is the immediate mechanical advantage this creates. If you run that exact same query average salary in NYC, the engine completely ignores the files for names, addresses, and phone numbers. It doesn't even touch them.
Because it doesn't need to.
Exactly. It only targets the city file and the salary file. It performs a rapid sequential scan of just those 12 gigabytes. So you instantly achieve a 40x reduction in disk reading simply by rearranging the geography of the data.
That's brilliant, just rearranging it. But isolating data by type doesn't just reduce the amount of stuff we have to read, right? The sources highlight that it also unlocks this massive advantage in how we actually compress the data.
Oh, absolutely. The compression is where it gets really powerful. See, when you store data in a traditional row, you are mixing completely different data types. You have a text string sitting right next to an integer, which is sitting next to a floating point decimal, and a timestamp.
It's just a jumble of formats.
Right. It creates what we call high entropy. It's chaotic. It's unpredictable. So if you apply a standard general-purpose compression algorithm to that, like LZ4 or GZIP, it really struggles.
Why does it struggle exactly?
Well, those algorithms look for repeated byte patterns to shrink the file, but mixed data types don't repeat cleanly. Best case scenario on a row store, you might cut the file size in half, you get a 2x compression.
Okay, 2x isn't bad, but I'm guessing columns do it better.
Way better, because once we switch to columns, we remove all that chaos. A file contains only one type of data. It's just a massive list of cities or a massive list of salaries. Nothing else.
And because the data is perfectly uniform, columnar databases don't have to rely on those general-purpose algorithms, do they?
Exactly. They use highly specialized domain encodings, so we aren't looking at a 2x reduction anymore. These encodings can yield 10x to 50x compression ratios.
Wait, 50x, explain how that math actually works. How do you shrink a file by 50 times just because it's a list of cities?
Okay, take dictionary encoding, for example. If you have a column of 1 billion cities, you're going to see the text string New York City millions of times, right? Storing that full text repeatedly takes up a massive storage footprint. So instead, the database creates a tiny little dictionary on the side. It assigns New York City the number 0. San Francisco becomes 1. London becomes 2.
Oh, that's smart.
Right. So the massive text file is instantly transformed into a highly compact array of tiny integers, which the computer can process infinitely faster.
Okay, that makes sense for text. But what if the data isn't text? What if it's just, a giant column of empty values or completely identical numbers?
Then the system might choose run length encoding, or RLE. If an employee database have a column for, say, severance package paid, and 99% of the time that value is 0, a column store doesn't physically write out 5,000 zeros in a row on the disk.
It would just be a waste of space.
Exactly. It just writes the number 0 once and attaches a small count saying, repeat this 5,000 times.
Oh, wow. That is incredibly efficient. But what about something like salaries, where the numbers are constantly varying, they aren't identical, and they aren't small dictionaries?
For varying numbers, they use something called frame of reference encoding, which is also known as delta encoding.
Yeah.
Imagine your company's base salary is $72,000.
Okay.
Instead of storing the massive 64-bit number, 72,050, and then 72,100 for the next person, the system just stores the minimum base value, the 72,000, in the metadata.
Oh, and then it just stores the difference.
Exactly. For the actual rows, it only records the offset. So just stores the number 50 and the number 100. It shrinks the physical footprint from huge 64-bit integers down to tiny 8-bit or 16-bit integers.
Okay, so we are taking these massive columns and basically shrink wrapping them into highly mathematically optimized blocks. But wait, if these columns are perfectly sorted and compressed so tightly, how do you add new data?
Yeah.
Because if I hire a new employee, I can't just shove their data into the middle of a completely shrink-wrapped file without, breaking all those delicate delta offsets and dictionary codes.
You've hit on the exact structural crisis that engineers faced in the mid-2000s. It's a problem called write amplification.
Write amplification.
Yeah. In a heavily compressed columnar file, inserting a single new row right in the middle means you literally have to decompress the entire file, insert the data, recalculate all the dictionaries and all the offsets, and then rewrite the whole file back to disk.
Just for one row, that sounds incredibly slow.
It's agonizingly slow.
It's like trying to swap out one block at the bottom of a perfectly balanced, completely shrink-wrapped Jenga tower without letting it fall. It's just physically impossible without rebuilding the whole structure.
That is exactly what it's like. So to solve this, a pioneering database architecture called CStore introduced a really brilliant compromise. They split the database engine into two distinct parts.
Okay.
They created a write store, which is an uncompressed, row-oriented buffer that just lives in the system memory. It is optimized purely to catch all new incoming data incredibly quickly.
So you just dump the new data there temporarily, prioritizing speed over organization, like a messy desk where you throw your mail.
Yes, exactly. And then you have the read store, which consists of those massive, compressed, immutable column files safely sitting on the disk. To bridge the gap between the two, CStore implemented a background process called the tuple mover.
Tuple mover. Sounds like a sci-fi gadget.
It kind of acts like one. Behind the scenes, while you are querying the database normally, the tuple mover quietly sweeps through that messy write store. It batches up the new data, sorts it, applies those extreme compressions we talked about, and seamlessly writes a brand new Columnar file to the read store.
That is so clever. But what about deleting data? Because if we can't insert a Jenga block easily, ripping one out of the middle has to be just as destructive.
It would be, yeah. So deleting uses a clever trick called delete vectors. A delete vector is essentially just a tiny separate bitmap file. When you delete a row, the database doesn't actually go into the compressed column to physically remove it.
It just leaves it there.
It leaves it there, but it flips a single bit in the delete vector from a 0 to a 1. And that serves as a flag that basically tells the engine, hey, when you read this column, pretend row 482 doesn't exist.
Oh, that's smart.
Yeah, it amortizes the cost of the deletion. It pushes all the heavy lifting of physically cleaning up the file to a background maintenance process that runs much later.
Okay, so CStore proved that we can manipulate flat, neat columns with incredible speed. But here's where it gets really interesting. By the 2010s, flat data was kind of becoming obsolete, right? Because the modern internet runs on messy, nested web documents like JSON files or API responses.
Exactly. The shape of data changed completely. We moved from these neat, flat spreadsheets to really complex trees of information.
Right. So if I have a user profile, and inside that profile is a list of 3 phone numbers, and inside those numbers are country codes, but the next user profile has 0 phone numbers. Translating that 3-dimensional nesting doll into a flat, 1-dimensional column list seems impossible.
It was a massive computer science problem at the time.
I mean, how does the database remember which phone number belongs to which user once everything is flattened out?
Right, because if a flat column has 3 phone numbers, followed by a null value, followed by 2 more phone numbers, a traditional column store has literally no way of knowing if that null value means the first user didn't have a 4th number, or if the second user had no numbers at all.
The relationships are just gone, destroyed.
Exactly. But then Google released a paper on a system called Dremel, which eventually evolved into the open-source Apache Parquet format that everyone uses today.
Okay.
Dremel solved this with a concept called repetition and definition levels.
The R and D levels, walk us through how those act as the map for the nesting doll.
Yeah, they are essentially 2 tiny integers that get stored right alongside every single value in the flat column. The definition level, the D level, solves the null problem. It records exactly how deep down the nested tree the path went before it hit a missing value.
So it tells the engine, we made it to the phone number array, but the specific country code was blank.
You got it, that's the D level.
And the repetition level.
The repetition level tells the engine at what level of the tree a value just repeated. So if you see a repetition level of 1, it means this new phone number belongs to the same user as the last phone number.
Okay.
But if you see a repetition level of 0, it means this phone number belongs to a completely new user profile.
So by just keeping track of these 2 tiny integers, which I assume compress beautifully, we can perfectly reconstruct the exact shape of a complex 3D document on the fly while still keeping the data in highly optimized 1D columns.
That's the magic of it. The overhead is almost non-existent, usually just 2 to 3 extra bits per value. But the impact was just monumental. Apache Parquet became the absolute standard for storing analytical data. But Parquet didn't just solve nesting. It introduced a physical file structure that optimized disk reading even further.
Right, the internal anatomy of a Parquet file. Our sources note it's broken down into row groups, column chunks, and data pages. But the real magic happens at the very edges of the file, specifically the metadata.
Yes. Every Parquet file contains what's called a file footer, which is a block of metadata. When a query engine approaches a Parquet file, it doesn't just start blindly reading from byte 0. It actually skips straight to the end and reads that footer first.
Wait, why at the end? Why not put the instruction manual at the beginning of the file?
It seems counterintuitive, right? But in distributed data systems, you are often streaming data sequentially. You don't actually know the minimum and maximum values of the data chunk until you finish writing it.
Oh, of course.
So you append all those vital statistics at the very end. The footer contains the exact minimum and maximum values for every single row group in the file.
So if I query the database for all sales that happened in October, the engine reads the footer and sees that, oh, row group A only contains dates from January to March.
And because it knows that, it completely bypasses row group A. It doesn't load it into memory. It doesn't spend a single CPU cycle looking at it. This is a crucial technique called predicate pushdown.
Predicate pushdown.
Yeah, you push the filtering logic all the way down to the physical storage layer, skipping vast chunks of data before they ever even leave the hard drive.
Incredible. So we conquered the disk, we compressed the data, we flattened the nested JSON, and we used metadata to skip anything irrelevant. Problem solved, right? End of story.
You would think so. But fixing one bottleneck in computing usually just exposes another one.
Yeah, actually.
While software engineers were perfecting the disk, hardware engineers were evolving the drives themselves. We saw the rise of NVMe, solid-state drives, and incredibly fast cloud networks.
Right, drives capable of reading like 7,000 megabytes a second.
At those speeds, the hard drive is no longer the slow part. The data is flying off the disk so fast that the bottleneck abruptly shifts. Suddenly, the CPU and the computer's RAM become the choke points.
Because the data is arriving at the processor faster than the processor can actually think about it.
Exactly.
And a massive reason for that CPU exhaustion is something called the serialization tax.
Yeah, the serialization tax was this hidden killer in data pipelines. Modern data ecosystems use a mix of programming languages. You might have a Java application extracting your data and then a Python tool doing the actual data science.
Which sounds totally normal.
It is, but historically, Java and Python conceptualize memory completely differently. A standard number in Java isn't just raw data. It's an object wrapped in 24 to 32 bytes of headers and garbage collection metadata.
So it's buried in all this proprietary packaging.
Heavy packaging. So to pass 10 gigabytes of data from Java to Python, the system couldn't just hand it over. It had to physically traverse the memory heap, unbox all the numbers, convert them into a generic flattened stream of bytes. That's the serialization part.
Right.
Then it sends them across a network socket, and then Python had to receive them, reparse every single byte, allocate new memory, and rebox them into Python objects.
It's literally like having a book written in English, and instead of just handing the physical book to the person sitting next to you, you translate the entire thing into French, then translate it into German, print a brand new copy, and hand it over. You've wasted hours and you haven't even read the book yet.
That is exactly what was happening. When engineers profiled these systems in production, they discovered that 80 to 90% of the total CPU time was being wasted just translating bytes back and forth between languages.
90%?
Yeah. And even when the CPU was finally ready to do the math, legacy databases crippled it with something called the Volcano iterator model.
How did that hold the CPU back?
Well, the Volcano iterator processed data row by row, passing data up a chain of operations one item at a time. It relied heavily on virtual function calls and if-and statements. But modern CPUs are designed to prefetch instructions to keep their pipelines full. They literally guess which branch of an if statement is going to happen next.
But if they guess wrong?
If they guess wrong, it's called a branch misprediction. The CPU has to dump all the work it prefetched, flush the pipeline, and start over from scratch. Processing row by row meant constant mispredictions and constant stalling, leaving over 90% of the processor's actual silicon capacity completely idle.
Wow. If we connect this to the bigger picture, this is exactly why companies realized they couldn't just throw more cloud servers at their legacy databases. They were scaling up the hardware, but the software physically couldn't use the CPU cores. They were CPU-bound, not disk-bound.
Spot on. And the solution to this hardware underutilization arrived in the form of two massive innovations. First, Apache Arrow. Arrow essentially did for computer memory what Parquet did for hard drives.
Okay, so it created a standardized format.
Yes, a standardized 64-byte aligned columnar layout for data strictly in the RAM.
A universal memory format.
Exactly. Java, Python, C++C, and Rust all agreed to adopt this exact same physical byte layout in memory. Because they all finally spoke the same language, that serialization tax completely vanished. They achieved zero-copy pointer sharing.
Meaning, instead of translating and copying the book, like in my analogy, Java just points Python to the exact memory address where the book already sits, and Python can read it instantly.
That's it. Passing 10 gigabytes of data between languages dropped from taking 10 seconds of heavy CPU translation to taking literal fractions of a microsecond. The data never actually moves.
Which frees up the CPU to finally do the math, which brings us to the second innovation, CMD, SIMD, single instruction, Multiple data.
CEMD is where modern vectorized engines like DuckDB and ClickHouse just leave legacy databases in the dust. Because Apache Arrow organizes the data in memory into perfect continuous arrays, the engine doesn't have to look at numbers one by one anymore. Modern CPUs have specialized vector registers like AVX512, which are literally just physically wider paths on the silicon.
So instead of telling the CPU, add salary A to salary B, then loop around and add salary C to salary D.
Right, you don't loop. You load a massive chunk of data into the vector register and execute one single hardware instruction. The CPU computes 16 integers simultaneously in a single clock cycle. It processes batches of thousands of elements flawlessly, keeping the CPU caches perfectly fed. No branch mispredictions, no stalling, just raw, contiguous math at the speed of silicon.
So we have completely reverse engineered the bottleneck here. We move from reading an entire row off a spinning disk to pulling highly compressed domain-encoded columns to skipping irrelevant data with Parquet footers to instantly sharing memory across languages with Arrow and computing 16 things at once with SIMD. Which brings us to the present day, the composable stack.
Yes. Because Apache Arrow standardized how we hold data in memory and Apache Parquet standardized how we hold it on disk, the tech world no longer needs to buy massive, closed-off monolithic databases from a single vendor.
You don't have to buy the entire car from one dealership anymore. You can buy the chassis from one place, drop in an engine from another, and swap the tires whenever you want.
The database has basically been unbundled into specialized layers. For physical storage, you use cheap cloud object storage, like AWS S3. On top of that, you place your data in Parquet files. But S3 is just dumb storage. It doesn't know how to manage a database, so you introduce a table format layer, like Apache Iceberg.
What exactly does Iceberg do in this Lego block setup?
Iceberg acts as the brain for your file storage. It provides ACV transactions. If a massive data pipeline fails halfway through writing 1,000 files, you don't want half-written, corrupt data polluting your analytics, right?
Right, that would be a nightmare.
So Iceberg uses clever manifest files to ensure that data updates are atomic. They either fully succeed or they fully roll back. It even allows you to time travel and query older snapshots of your data.
That's super useful. And then when you actually want to ask a question of this data, you bring in your query engine.
Exactly. You point a vectorized engine like DuckDB or Data Fusion at the Iceberg tables. The engine reads the Iceberg manifests, uses those stats to prune the Parquet files, pulls only the columns it needs, decodes them directly into Apache Arrow memory buffers without copying a single byte, and runs multi-lane SIMD hardware operations to deliver the answer in milliseconds.
So what does this all mean? For the listener who is building a data platform or trying to optimize their company's tech stack, why is this modular approach so critical today?
It means zero-copy composability. It is the definitive end of vendor lock-in. If a brilliant startup invents a query engine tomorrow that is twice as fast as what you use today, you don't have to spend a year migrating your data to their proprietary system.
You just swap out the engine.
You swap it out like a Lego block, point it at your existing open-source Parquet files, and it works instantly. The barrier to entry has evaporated.
That is massive. So, to quickly recap the journey we've taken today, simply pivoting our data layout from rows to columns cuts disk I/O exponentially because we only grab the specific data we actually need. Because identical data is grouped together, we achieve extreme compression using domain encodings like dictionaries and delta offsets.
Yep.
We handle messy web data using repetition and definition levels. And finally, by standardizing our in-memory formats with Apache Arrow, we unlock zero copy sharing and multi-lane SIMD processor speeds.
It's a completely different world now. And, this raises an important question.
Let's hear.
Think about the broader implications for the tech industry. Historically, massive technology giants built their empires on the back of proprietary, highly optimized, locked-in databases. Their competitive moat was that their infrastructure was simply faster than everyone else's. But today, the entire analytical stack, from storage formats like Parquet to memory formats like Arrow, is built on shared, open-source standards that literally anyone can plug and play. If extreme speed and efficiency are no longer a secret weapon, but just a free baseline standard, how will the next generation of applications differentiate themselves? The moat has been completely filled in.
If speed is just a commodity now, the playing field is entirely leveled. It is certainly something to think about the next time you're sitting in front of a dashboard, watching a loading spinner. That lag isn't a limitation of the hardware anymore. It's a choice of architecture. Keep digging deeper into the data that runs your world. Thank you for joining us on this deep dive into the architectural engine of modern analytics. Catch you next time.